What is the golden rectangle? The golden rectangle is known as the most aesthetically pleasing rectangle. For a rectangle to be the golden rectangle, the length of the base has a specific numerical relationship to the length of the height. If you were to choose one of the rectangles below, which is the most appealing? Most people would have chosen either the green or the red one. That is because they both represent the golden rectangle. The golden ratio. The golden rectangle has an interesting connection to the Fibonacci sequence. To refresh your memory, the sequence is 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. If we were to divide each number by the previous one, for example, 1 divided by 1, 2 divided by 1, 3 divided by 2, or 89 divided by 55, and 144 divided by 89, the sequence of quotients would be 1, 2, 1.5, 1.6182, and 1.6180. The quotients seem to increase, then decrease, then increase again, and then decrease until they reach the golden ratio of 1.618. The golden ratio is noted as the Greek letter phi, and it gets its name because it satisfies the symmetrical equation of ratios. Phi divided by 1 equals 1 divided by phi minus 1. The number that describes the golden ratio is phi equals 1 plus square root of 5 divided by 2, which would give us 1.618. There must be some way to calculate the ratios in a golden rectangle. A golden rectangle is any rectangle having base b and height h, so that b divided by h equals phi equals 1 plus square root of 5 divided by 2.
When we look at a golden rectangle, we do not realize that there are smaller golden rectangles within the one big golden rectangle. When you take the biggest square possible out of a golden rectangle, you are left with another rectangle left over. The smaller rectangle is also a golden rectangle. Then, looking at that smaller rectangle, if you take the biggest square out of that rectangle, you are left with an even smaller golden rectangle. This process continues to repeat as the rectangle gets smaller. This is the property of the golden rectangle. This property, as stated in the Heart of Mathematics textbook, reads that at any stage in this process, no matter how small the golden rectangle is, when we cut out the biggest square possible, we have created an even smaller golden rectangle.
We want to prove that the smaller rectangle in this golden rectangle is a golden rectangle as well. We take a look at this diagram. Golden rectangle AEFD is made up of one square and another rectangle, and we want to prove that this rectangle is the golden rectangle. So square ABCD is combined with rectangle BEFC to create one big golden rectangle. We know that there is a 1 to 1.68, or phi, ratio in a golden rectangle. We know this because AD equals 1 unit and AE equals phi. We want to prove that rectangle BEFC is a golden rectangle. Therefore, we need to show that the ratio of its longer side to its shorter side, or EF divided by BE, is phi. First, we need to find the lengths of the sides of the smaller rectangle. Since EF equals AD, then EF must equal 1. To find BE, we know that BE equals AE minus AB. Because AE equals phi and AB equals 1, then that must mean that BE equals phi minus 1. So, the ratio is now EF divided by BE equals 1 divided by phi minus 1. This relates to our equation from earlier in this report, which we know that phi divided by 1 equals 1 divided by phi minus 1. Therefore, we can now solve that EF divided by BE equals phi. We can now conclude that the small rectangle BEFC is in fact a golden rectangle, which completes our proof. We have to ask ourselves, how do we know if this golden rectangle is really the golden rectangle? We want to prove that rectangle AEFD is really a golden rectangle. To find this, we first have to prove that the length of AE divided by the length of AD is equal to the golden ratio, which is 1 plus the square root of 5 divided by 2. Note that the size of the golden rectangle does not matter. It's the ratio of the two sides that matters. When trying to solve the missing sides of a golden rectangle, we must first learn how to properly construct this perfect rectangle. The first step is to start by building a square. This square must have all sides equal in length and all angles at 90 degrees. We will call this square ABCD. The length of AD, which we think of as being 1 unit, can now completely determine the length of all the other sides of the square because they should all have equal sides due to what the property of a square is. Knowing side AD helps find everything else in the rectangle and can be used as a reference since we know the ratio of a golden rectangle is 1 to 1.618. The second step is to connect the midpoint of the base of the square with the northeast corner of the square, connecting with a straight line segment, creating a right triangle within the square. Extend a line from the base out to the right as well. This point that bisects side AB we will call M, and this angled line segment we will call MC. Because this line bisects side AB, we know that the length of AM and the length of AB are both 1/2. The third step is to draw a curved line, almost making a circle, which the midpoint of the base and the radius of the base extends all the way to the northeast corner of the square we have. The goal is to figure out the length of AE. We know that AE equals AM plus ME. We already know that AM equals M divided by B, which equals 1/2 because M bisects the bottom side of the square in the rectangle. Note that the length of ME is mysterious. We still don't know that. To complete the rectangle structure, the final step is to draw a line that is perpendicular to the landing strip and that also passes through the point where the circle hits the landing strip. The perfect golden rectangle should now be made and constructed if the previous steps were done correctly. To continue the proof, we know that segments MC and ME are the radii for the same circle, therefore their segments must have the same length. Using the Pythagorean theorem, we can figure out the length of MC because a triangle is formed in the rectangle. Since we know line segments BC squared plus MB squared equal MC squared, we can substitute these in as 1 squared plus 1/2 squared equals MC squared. We then simplify to 1 plus 1/4 equals MC squared, or 5/4 equal MC squared. As a result, MC equals the square root of 5 divided by 2. Therefore, ME also equals the square root of 5 divided by 2. With this, we can put together that AE equals 1/2 plus the square root of 5 divided by 2 equals 1 plus the square root of 5 all over 2. The final solution of AE divided by AD is AE divided by AD equals 1 plus the square root of 5 all over 2, all of that divided by 1. This equation then simplifies to 1 plus the square root of 5 all divided by 2, which is the same as phi. Because we have the golden ratio, this proves that we have constructed a perfect
To bring
golden
these examples into the real world, we have created a few problems to tie everything together. The first problem states that suppose you have a golden rectangle cut out of a piece of paper. Now suppose you fold it in half along its base and then in half along its width. You have just created a new smaller rectangle. Is that rectangle a golden rectangle? The solution to this problem is yes. This rectangle is a golden rectangle because you are dividing each side by half, which is equal on each side to make a smaller golden rectangle. Since b over h equals 1 plus the square root of 5 over 2, we can say that b equals 1 plus the square root of 5 and h equals 2. When we divide each by a half, we get a ratio of 1 to 1 plus the square root of 5 over 2, or p, which is the golden ratio. For a rectangle to be a golden rectangle, it must contain the golden ratio in its size. The second problem states, let G be a golden rectangle having base b and height h. and let G be the smaller golden rectangle made by removing the largest square possible from G. Compute the ratio of the area of G to the area of G. That is, compute area G divided by area G. Does your answer really depend on B and H, the original size of G? Are you surprised by your answer? The solution to this problem is, since B is the base and H is the height, we can assume that the golden ratio applies here. Therefore, the area of G is pH times h, which is simplified to pH squared. Since we get a smaller golden rectangle by removing the largest square possible from G, we know that the longer side of the smaller rectangle is also h. Since we put b in the terms of h, we can split up the base of G into a square with the base of h and the short side of the smaller golden rectangle G. Has base b minus h, or pH minus h, in terms of h. Therefore, the area of G is h pH minus h. The ratio of the area is